Hello, everyone. We present our project DS Fusion Artistic Typography via Discriminated and Stylized Diffusion. First, we give a short overview of typography. Wikipedia defines typography as the art and technique of arranging type to make written language legible, readable, and appealing when displayed. While human artists are able to produce stunning typographies that incorporate semantics into fonts very creatively, as shown by the few examples on screen, doing so automatically proves to have many challenges. Our task in DS Fusion is thus, given a character, font, or glyph, we take as input a style word whose semantics are then incorporated into the resulting typography. We introduce in our project a novel method to automatically generate an artistic typography. We have an assortment of challenges, including conflicting goals, that is, artistic stylization versus legibility, lack of a ground truth, and an immense search space. Our model is coined DS Fusion for Discriminated and Stylized Diffusion. Our key idea is therefore to employ adversarial learning with diffusion to provide an implicit guidance to the generation. To train diffusion models, noise is first added to an image through a forward process. This noisy image is then sent to the denoising process in a diffusion model, which is typically modeled by using a U-Net. The model then works to remove the noise from the image, most often under a textual condition. Latent diffusion models work the same way as diffusion models in removing noise from the input. However, they work in latent space as opposed to pixel space. This greatly reduces the model size. We use latent diffusion model as the backbone generator in DS Fusion. Our method takes as input a style word in text, which may optionally also include an attribute. The first step in our pipeline is to generate a set of style images using latent diffusion model. This set of style images works to regulate the denoising generator and acts as a visual representation of the textual input. Afterwards, both style and glyph images are encoded into latent space using encoder of the latent diffusion model. Noise is added to latents of style images and a diffusion loss is applied on the denoised output. Condition vector here is the output of BERT, where the input of BERT is the style prompt concatenated with the glyph. A CNN discriminator then works to implicitly guide the generated outputs towards the shape of the glyph image. Since there are no target images available in this task, the generated results can only be supervised implicitly. Finally, once the training is done, at inference, given a style prompt and the glyph, the denoising generator produces outputs in latent space, which can then be decoded to produce a range of output images. Here we show some results using a single letter input to our DS Fusion model. Here we show some results in one font versus multiple font training. Results show a stronger legibility in the former and a more abstract stylization in the latter. DS Fusion demonstrates its ability to utilize all the letters of a word to convey semantic features in a creative manner. We show here some results by giving multiple letters as input to DS Fusion. Here we show some results produced by varying the fonts of the input glyphs for dragon plus the letter R. They highlight the ability of our method to preserve various shape characteristics of the input. The use of style attributes in the input prompts can also be an effective means to further customize the stylization. Here we show some visual comparisons with Google Search, Stable Diffusion, ClipDraw, and DALL-E2. We do 2 user studies. In the first study, we compare our method with other generative methods, including DALL-E2, ClipDraw, and Stable Diffusion. The users are shown 4 images generated by each method and are asked to choose the image that best corresponds to the typography requirements. We show that DS Fusion clearly outperforms the other methods in this case. In the second user study, we compare our results with artist-crafted results. We found that in about 42% of the cases, users found our results better or equivalent to that of human-designed examples. This is a satisfactory outcome since human-designed examples heavily rely on the creativity and expertise of designers. And that's it. Thank you very much for watching.